All right, class, let's continue section 2.3 with graphing polynomial functions. So what we're going to do now, we're going to put the first derivative and the second derivative to good use. We're going to make a sign diagram for the first derivative, a sign diagram for the second derivative, draw all the conclusions, and then we're on our way to get a super good graph. Okay, so that's exactly, so we're going all the way. That's exactly what you guys are going to have to do on the test. First derivative, second derivative, sign diagrams, draw a graph. Okay, so let's get started. First derivative. It's a 3x squared minus 3, yes? Find the critical numbers, right? How? Set the first derivative equal to 0, which you can. Solve this quadratic equation easily. X will equal plus minus 1, right? Divide by 3, take the square root, easily done. So these are your two critical numbers. Make a sign diagram. Okay, there's x, here's its derivative, and here is the function. Let's see what conclusions we draw out of it. So I'm going to, same as we did in 2.1, place my critical numbers in order from left to right on the number line as they come. So what happens to the first derivative at these points? The first derivative is equal to 0. What about signs? What are the signs of the first derivative? Well, here it is. Let's pick a number between -1 and 0, and that would be 0. I'm sorry, between -1 and 1, and that'd be 0. Plug it in here, you're going to get a negative value, yes? Put in a number more than 1, let's say a 2. That's a 4. 12, that's going to be a positive, right? -3 stays positive. Pick a number here, let's say -2. -2 squared is also a 4. 12 minus 3 is 9. That's also a positive. So really, as I said, the signs are alternating. So what kind of conclusions can we draw about our function? Well, first derivative positive means the function's increasing. First derivative is 0, means the graph is going to even out, yes? Then it's going to go down, even out, and then it's going to go up. Okay. Let's see about the second derivative. Now, the derivative of the second derivative, the second derivative of the function, or the derivative of the first derivative, that's what I meant to say, is just 6x. Good. Find the, whatever, critical number, possible inflection points, yes? So what we're going to do is we're going to set this equal to 0, and then the solution is super easy. That's just a 0. So let's make a sign diagram for the second derivative. So from -infinity to +infinity along the number line, there's only one place of interest. What happens with the second derivative? What happens to the function itself? Okay. Now, the second derivative is 0 when x is 0. Before that, any value you plug in from -infinity to 0, let's say -1. 6 times -1 is a negative, yes? Pick a number to the right of 0, let's say +1. Plug it in, that's going to make it a positive. Now, what does that mean for the function itself? Well, second derivative a negative, that means a sad face. Second derivative a positive, that means a happy face. As you see, we change from negative to positive. That means we're getting an inflection point in between, yes? So the graph is going to change inflections there. Okay. And if anything, look at this one here. Does that mimic what this graph, or what this conclusion here is mimicking as well? We go up, down. Yes, it's turned upside down. It's turned up. All we know is that in between here, we're going to get an inflection point. Okay. First derivative, second derivative. Here are my sign diagrams for each of those. Yes, I'm drawing my conclusions. What are the conclusions? This is concave down. This is concave up. This one's increasing. Yes, decreasing. Increasing again on this interval. So all sorts of things I'm finding. If this is increasing then to decreasing, that's going to be a maximum point here, and I'm going to reach a minimum point here, right? So all sorts of information hidden right there. Well, not hidden anymore, we figured out. Okay, what do I need to do? I know when things are happening for which x's, but I don't know how high this is going to happen. So I need to take these critical numbers, -1, 1, and 0, and turn them into points. So I'm going to make myself a table of values for my function. Okay. So what numbers I'm interested in? I'm interested in -1, 1, and 0. These are the numbers of interest. Okay. Plug these numbers into the function itself. So -1 cubed is -1. -3 times -1 is a +3. So -1 plus 3 is 2 plus 2, that's a 4. Okay, do the same thing for 1. 1 minus 3 plus 2, that's going to be a 0. Plug in a 0, you'll get a 2. Okay, and now, happy drawing. Okay, so what do I know? I have the point of coordinates -1, +4. By the way, I hope I did this right. Yeah. I have the point of coordinates 1, 0. And in between, I have the point of coordinates 0, 2. Okay. So what do I know about my function? I know my function is going to be increasing until I reach this x of -1, by the way, yes? So my function is going to go up until I reach this point. What does it do? It's going to start coming down, yes? There's a maximum point there, okay? What happens, by the way, between -1 and 1, there's 0. What happens in 0? I have an inflection point. That means what? My graph is going to start turning the other way, right? This was concave down, and about here, it's where it starts going on the upturn, okay? Until I reach this point where x is 1. That's a minimum value. There it is. That's it. There's no other points of interest. Nothing else funny is going to happen. After that, it's just going to keep going down, going up. So here's my maximum. Here's my minimum. By the way, these are local mins and local maximums. They're not absolute, right? They're not the absolute highest. Here's my inflection point. We're good to go. All done. All right. This one should be a little bit more involved. It's a little bit of an uglier function. But we'll do the same thing. I want to graph this function, go through first derivative, second derivative, and see what information it's hiding. So, first derivative, 3 times 4 is 12, x cubed, minus 48, x squared, plus 36, x. Great. Set this equal to 0, right? It's not going to be undefined, but it can be 0. Solving this cubic equation, let's see if we can factor, and sure enough, 12x is the greatest common factor, times an x squared minus 4x, and then plus 3. Can we factor this some more? Sure enough, numbers to multiply to 3 and add to 4 are 1 and 3, both with a negative. So the critical numbers, as you see, are x equals to 0, x equals to 1, and x equals to 3. Okay, so let's put these in order to make a sign diagram. Okay, so from negative infinity to positive infinity, in which order do they come? First of all, comes 0, then 1, and then 3. Now, what do we know about those? We know that the first derivative is 0 at any of these points, yes? And then I need the signs. That's why it's called a sign diagram. So the first derivative is going to be, I don't know, let me pick a value. How about -1? That's a -12 times -2 times -4, 3 negatives, that's a negative. And I'm not going to waste even more of your time. The signs are alternating, as I said. If your factors are linear, in other words, to the power of 1, then the signs will go alternating. Now, what does that mean for the function itself? It means the function itself, or the yeah, the graph of the function itself first comes down, then evens out, then goes up, then evens out, then comes down, then evens out, and then goes up quite a bit. Plus, by the way, if you remember anything from college algebra, you've learned that a fourth degree polynomial function will have the same end behavior as a quadratic function. So just like a quadratic function will start and end up here, it will turn at most 3 times, one less than the degree. So here are my turning points, 1, 2, 3, yes, and possibly it will cross the x-axis 4 times. I might get 4 solutions for this equation if I could solve it. Okay, all right. So let's see, second derivative. So for now, I have an idea of what the graph looks like, right? Perfect. It's coming to a min at 0, a max at 1, and another min at 3. So let's find the second derivative and see what else we could tell. The second derivative is going to be a 36x squared minus 96x plus 36. Okay. Can we factor something? Yes, I can factor out a 12. 12 goes into 96 8 times. All right, and this is not going to be factorable, okay? So if it's not going to be factorable, how else do I solve this equation? Well, quadratic formula. And by the way, there's only so much we can make factorable for you. If I tried to set this up so that the first derivative is something factorable, you're not gonna get it to where the second derivative is factorable as well, okay? It's just good luck only goes so far. Okay, so a plus or minus b squared, which is 8 squared minus 4 times 3 over 2 times 3. Plug it in, that's going to be an 8 plus or minus the square root of 64 minus 36, that's 28, divided by 6. And as you see, this is not a perfect square, which is why this wasn't factorable, right? So put in a calculator, 8 plus the square root of 28 divided by 6. By the way, I already did that. So I'm going to get 2 answers. One of them is 2.2-ish. And the other one with the negative is going to be about 0.45. That's what I have, 5-ish. Okay. All right, so let's make a sign diagram. Okay. For the second derivative. And then draw conclusions for your function itself. Okay. So from negative infinity to positive infinity, first comes the 0.45, then comes the 2.2. Now, the second derivative we know was 0 there. That's how we found them. Let's pick some values in between. So less than 0.45 is 0. Plug it into the second derivative, you'll see you'll get a positive, right? Then it's going to be alternating again, negative and then positive. Again, put in a 1. You'll see you'll get a negative. Put in a 3, you'll see you'll get a negative. You could just believe me. Again, the signs will be alternating. So a positive second derivative means a happy face. A negative second derivative means a sad face. And a positive second derivative means a happy face again. A 0 second derivative simply means that there could be an inflection point. It's not, doesn't mean the graph evens out. So like in the case of a first derivative, okay? So horizontal, a 0 first derivative, so if the first derivative is equal to 0, means you have a horizontal tangent line. If the second derivative equals to 0, it simply means that you have a possible change in inflections, okay? That's all. Possible, right? Okay, so let's put all this information. So does that graph or this conclusion here kind of match the conclusion here? Looking up, looking down, looking up again. Yes, look at that. So definitely we're getting inflection points in between. Why? because the second derivative changes signs left and right of it. Okay. So let me do what? What else do I have to do? I have to make a table of values, right? For this function. So I'm going to go up down here again and make a table of values with my very many important points. What important points do I have? 0, 1, 3. Then on top of that, 0.45 and 2.2. So quite a lot of points of interest in here. So you plug it into your function itself, right? Plugging in a 0, you actually get a 0. Yes. Plugging in a 1, 3 minus 16 plus 18, you'll get a 5 easily. Plugging in a 3 is not quite as fast, but I plugged it in already, and I have a negative 27. 0.45 to the 4th times 3, again, this is going to take a long time. That's about 2.31, already did that. And when you plug in a 2.2, same thing, takes a little bit of, just enter in your calculator, press enter once, and you got it. But the important thing is that you plug it into your function, yes. Okay. That's the one we're drawing or graphing. So I see I'm already more on the negative side, so I'm going to be prepared and make my graph go rather down. Then up. Pencil would have been good. It's just my desk made my line wobbly. Okay, so what points do I have? I have 0. As you see, that's why I went more on the positive side. 1, 2, 3. Things are happening. 0.45 is about here. And 2.2 is about here. Okay, what are the y values I'm getting? I'm going to get a 5, which I'm going to put up here. And remember what I said, that, 1 second, 30, counting down. Remember what I said, that the units you're using for the y-axis are could be different than the units you're using for the x-axis. So this is a 1 on the x-axis, whereas a 1 on the y-axis only is about this tiny. Yes, so you can, as long as you scale it consistently with each other. So if this is a 1, then clearly there's a 2. So these are spaced out exactly evenly. Yes. And these are spaced exactly nice and evenly. So if that's a 5, this could not be negative 20, right? So the x-axis is consistent with itself. The y-axis is consistent with itself. So let's see about my graph. This is what I know. That's not 15. That's your negative 1, and that's your 5. Okay. So I know 0, 0. I know 1 goes with 5. I know 3 goes with negative 27, which is about down here. Okay, 3 goes with negative 27. 0.45 goes with 2.31, so just about here. Then what else? And then 2.2 goes with negative 13.5, about here. Okay, so what happens to this graph? This graph first is coming down until I'm reaching 0, 0. So there it is. And it first looks up, right? And it looks up until about this 0.45. Then what happens? It's starting to turn the other way, right? Starting to be concave down until I reach this maximum point at 1. Then the graph goes down, right? It's going to go down all the way until I hit the 3, but before that at 2.2, the graph is starting to look the other way. So it's an inflection point. Turning down, turning back up. Okay, here's your graph. What do I have? I have a min, I have a max, I have another min, I have an inflection point here, and I have an inflection point there as well. Okay, right here. Okay, here's the graph. Okay. All right, so again, this is what you guys are going to have to do. I know, as I said already, the textbook, some of those graphs, the examples in the textbook would try to be putting a lot more detail in it just to explain what I have said in words for you right here, right? I didn't, but in the textbook, you don't hear my words, you have to see them written. So that's why those examples could look a little bit longer, because again, everything is in detail explained for you where things are coming from, okay? But on the paper, it looks pretty enough, okay? All right, so in other words, on a test, that's exactly what you'll have to do and no more, okay? All right, so last thing for this section here, almost done. This is a good exercise without the function, but basically with these conditions. So what I'm telling you is this, okay? I'm kind of telling you derivative is positive, negative, positive, 0. Second derivative is this. So I'm kind of just giving you the sign diagram, and without any further points, and with the sign diagram only, could you tell what the graph looks like? Sure enough. So that's exactly what I'm giving you here. So it says, given the following conditions, sketch a possible graph for this function. So let's see what I'm giving you. I'm giving you a point, kind of like that table of values that we make up when we're ready to graph the function. So let me get started here. We're gonna have to graph a possible function, and it might look a little bit different for each of you, but as long as these conditions are satisfied, I am satisfied. Okay, so here it is. F of 3 is equal to 2. What does that mean? That's a point on the graph, yes? So that's one point that definitely my graph has to go through. When x is 3, yes, f of 3 means x is 3. The y value is 2. So that simply means the point on the graph that I have has coordinates 3, 2. So whatever else you might do to this graph, it has to go through here, right? Okay, the derivative at 3 is 0. That means what? At this point here, there's going to have to be a horizontal tangent line. So I'm saying that at this point, either you have a minimum value or you have a maximum value. The first derivative is greater than 0. What does it mean greater than 0? It means positive, yes? From negative infinity to 3. And less than 0 means what? A negative from 3 on out. So if you want, you can even make yourself that table of values, that sign diagram that says what about your first derivative? That something happens between negative infinity and 3. What happens between negative infinity and 3? It's a positive, yes? From 3 to infinity, yes, your first derivative is a negative. And what happens exactly at 3? It's a 0, yes? So basically, I'm giving you in words a sign diagram. Now, knowing that, what conclusion do we draw about our function itself? That it's going to go up, that it will even out, and then it's going to go down. So it's going to go up, it's going to even out, then it's going to go down. Simple. Okay? Now, how could it look differently? Maybe you made it go up tighter, right? Maybe you made it go this way, right? But the point is, you can't do anything else. You can't make it turn again, because why? It says it's negative from 3 to infinity, so it's just going to have to keep on going down. Nothing else, right? So yeah, keep it simple. Right, this is a little bit more. It doesn't say, you can make it have a hole, by the way, right? It didn't say continuous or anything like that. You can make it have a hole. You can make it go down, jump, and then go down some more. It's up to you. But as I said, keep it simple. Don't make more than what you need. Okay, so here it is. Let's try another one. F of 0 is equal to 3. Again, that simply means a point on your graph. What point is it? If x is 0, y is 3. x is 0, y is 3. So right here, I'm going to have to make the graph get through this one point, if anything. Okay. Maybe I should do the sign diagram. What do you guys think about the first derivative? Okay. So it says the first derivative is positive. Yes, more than 0 again means a positive. From negative infinity to negative 5. I'm going to skip over this. It's less than 0, so negative, from negative 5 to 1. And then from 1 to infinity is going to be positive again. So it looks like this is where my changes are, right? So I only go from negative infinity, to negative 5, negative 5 to 1, and then 1 to infinity. So my breaks, my sign changes are at negative 5 and 1, right? These are my critical numbers. Okay. And that's about all on the first derivative. Okay. So it doesn't say that the function's evening out, but at least I know it goes up, it goes down, and then it goes up again. Okay. And it didn't say it's not evening out. So let's see what's further, and then if we can make that conclusion. Do we need to make crazy things like gaps and holes, or could we just keep it simple and just make it round? Yes. So again, it didn't say it's gonna be 0, but it doesn't mean it's not, right? There's nothing in here that says it cannot equal to 0 at negative 5 and 1. The second derivative, let's make a sign diagram for that as well. I'm gonna make it down here. It says from negative 2 to infinity, it's more than 0, so it's a positive, and it's less than 0, so a negative, from negative infinity to negative 2. So at negative 2 is switching. Okay. Now again, what does that mean for the function itself? That means it's going to be concave down, which totally makes sense, yes, and then concave up again. So at negative 2, I definitely have an inflection point. Okay. And then f is continuous and differentiable everywhere. What does this statement mean, continuous and differentiable? Continuous means no gaps. Yes, no holes. So nice curve, yes. Differentiable means when is a function not differentiable? It's not differentiable if it's not continuous, but we already know that's not true. If it comes to a corner, so because it says differentiable, also it means no corners or vertical tangent line. So it's going to be a nice smooth curve like a polynomial function. Okay, that's it. So the one thing that we don't have, it's the y values. So I know that it's going to do what? I know the graph is going to go up until x is a negative 5. 1, 2, 3, 4, negative 5. Okay. But what's the y value? We don't know. We can make it as high as we want, right? So everyone's graph can be slightly different. But we know up to negative 5, the graph is going to go up. We know the other point of interest is 1. That's where we have a min. Okay. And we know at negative 2, we have an inflection point. Okay, so let me draw this. And remember, this is a point that's I'm gonna have to go through, okay? So this is gonna be a min at 1. I'm gonna have a min. Okay. All right, so the graph is going to go up, right? Until it reaches a negative 5, yes? Then, I might want to make it go up more. Then it's gonna, at negative 5, then it's gonna have to start coming down, yes? What happens at negative 2? Negative 2, it's starting to turn back up. I have to make it go through here. And then it turns up. what I needed to do, make this higher. So I have room to come down, go through negative, go through 0, 3, and reach my minimum here. Okay, so a pencil definitely helps. But let's see, do I have my conclusions? I have a max at -5. I have a min at 1. I had to make it go through 0, 3, right? This was the 1 point only on the graph that I had to hold on to. And by -2, the graph had to start turning the other way. Okay, so there you have it. So I'm saying a pencil might help, and a little bit more room on the paper, of course, because just to make it come down and have a min here, right? Start turning, I needed a little bit more space. Okay, and finally, this is it, last one. F of 0 is equal to 5. Okay. F of 0 is equal to 5. This is 1 point on my graph, right? Okay. The first derivative switches from -infinity, there's something up to -3, oops, and 0 and 3, and then infinity. So it looks to me stuff is happening, -infinity to -3, then again from 0 to 3, then -3 to 0, and 3 to infinity. So I have the whole thing counted for, and what happens to this first derivative? First, it's less than 0, so it's a negative. And then a negative again from 0 to 3. And then more than 0 means a what? A positive. And then a positive again from 3 to infinity. So we're switching. Probably, I'm guessing it's equal to 0, but it doesn't have to be. So what conclusions am I drawing about my function itself based on this alone? That it's going to come down, up. So at -3, I have a min for sure. At 0, I'm going to have a max, because then the graph goes back down. And then it's going to come down up until I reach a 3, and then it's going to go up. Okay, all right. The second derivative, okay, let me make a sign diagram for that second derivative. It really helps visually, then you can draw it better. That's what I think. You don't have to do that, but it helps me. So something's happening from 0 to infinity, and something else from -infinity to 0, right? So I see there's only one break. Okay, what is it? The second derivative is more than 0, means positive on 0 infinity. And then, oh, and positive again. It doesn't say negative, right? So it's positive from 0 to infinity and from -infinity to 0. So what does that mean for the function itself? It means it's going to be concave up and concave up. Okay, concave up and concave up. It doesn't turn back down. Okay. So, clear enough, because we're not changing concavity, so it doesn't turn the other way. The no turning part really means that there's not going to be an inflection point. So as you see here, f is continuous and differentiable everywhere except for x equals to 0. So it's not continuous at 0, and it's not, I think what I meant here, f is continuous. Okay, well, fine. Okay, so this is what I'm saying. I might have missed the comma there. It's continuous and it's continuous and differentiable everywhere except for x equals to 0. So not continuous at 0, yet we have a point at 0. Because if not, I would have had a vertical asymptote, no problem, right? But I don't have a vertical asymptote, so I have to, okay, fine, I know what I'm going to do. Okay, this is what I'm going to do. If it's not continuous, yet I have a point, I'm going to make a break in the graph. Okay, so what happens to this? The points of interest are -3, and of course at 0, and +3. 3. Okay, so I know at negative 3 I have a min, and I know at 3 I have a min. Okay, so this is what's going to happen to my graph. I'm going to make it come down until I reach negative 3, and then I'm going to make it go up. Yes. As you see, it's concave up the whole time. Yes. There's only concave up. The fact that it's not differentiable, it could mean a corner point, but the fact that it's not, if I continue down here, then I'm going to make it continuous. Yes. So I have to make it a gap. Okay. So f of 0 is 5, right? That's the point included when x is 0, so I'm not including this point. Okay. What else is happening? From 0 up to 3, and again, see, it says between 0 and 3, not at 0, right? So in between 0 and 3, the function again is going to go down, and then it's going to go up again. Okay, so I have a min and a min at negative 3 and at 3. Perfect, I satisfied all the conditions. That's pretty cool. All right, so you'll have a few of these to play with for homework. Let's see what it looks like. It's actually pretty fun. Make sure all conditions are satisfied, and as I said, it really helps me translate this into a sign diagram, because then the problem looks pretty much like the ones that we just did right before, right? Where we have the function and we make the sign diagrams and we draw our conclusions. So quite a fun section, I'd say. Okay.